All right, so we've all seen this many times, so I won't belabor the point, but this talk will also, like some previous talks, be talking about how do you run code in adversarial environments when your data is sensitive. So you have a user, you have a server, the user wants to run some function f on its data, but it does not want the server, and it wants the server to do this because it takes a lot of time, but it does not want the server to learn anything about the data or the result. And as has also been said, the cloud is not this pretty picture, the server is not this pretty picture, it's apps running on OS, running on VMs, which run on complicated hardware stacks, including execution engines, multi-levels of cache, tertiary services, networking, compute disk. There's stacks of these, and the adversary can be in the hardware, the OS, the VMM, the applications, the tertiary services, etc. So what can go wrong? Well, what can go wrong in lieu of all these adversaries is that when you run a program on the remote server, it has data-dependent interactions with the system stack. So that's going to be the focus of this talk. So when a program runs, it's going to have data-dependent exceptions. This is like it can figure out when a divide by zero happens or when a page fault happens. It can also have data-dependent software API calls like system calls. And finally, as has been pointed out in previous talks, it has data-dependent hardware resource utilizations. The hardware is only used when it's actually needed. And this can all leak based on when these events happen, what auxiliary information they contain, like syscall arguments, and in what sequence they happen. So the twist I'm going to put on this talk is I'll be discussing defense mechanisms that we can apply using only commercial off-the-shelf hardware, hence the systems angle of the talk. And the goal will be to defend against remote software adversaries. So just to be clear about the threat model, so Divya said that we should always have a threat model. So here's the threat model. So on the one hand, we have what is the user program? Is it public or private? So we'll be, so public is like it's an Amazon AWS service. It's known to the cloud can study it offline. Private is like it's a confidential program. Then we have a space of trusted computing bases on the server. We can go all the way up to not trusting anything on the server, to trusting the COTS hardware, and then trusting different modicums of software that are running on the server, the user application, the runtime, all the way down to supervisor software like the operating system. And then finally we have our adversary, a remote software, either user level or supervisor level adversary. So this talk will be focusing on public programs. So this is a very dangerous threat model. The adversary can study the program offline. This is like crypto routines. It's like a stronger adversary. And on the server side, we'll permit to be in our TCB anything up to the supervisor software, which is kind of when the number of lines of code in the trusted computing base falls off a cliff. And both of these adversaries. All right, so the rest of the talk is 3 parts. Here is part 1. So we'll start on a positive note. And that is that we can actually do many interesting things with COTS hardware today. So the kind of most direct example are trusted execution technology extensions, which have emerged in the last decade or so from main vendors. So this is like ARM Trust Zone, more recently Intel SGX. And what these services allow us to do is wrap sensitive applications in virtually isolated containers that are backed with a hardware guarantee. What does that mean? That means that when I run sensitive code in these containers, there cannot be direct inspection from adversarial supervisor software like the operating system or direct tampering. Now, a secondary benefit that these, quote, virtually isolated containers give us, especially in the case of Intel SGX, is that we can define explicit interfaces between untrusted and trusted code. So this is really useful when talking about composability, taking a bunch of small modularized containers and composing a larger system out of them, because you know exactly how the adversary can talk to the trusted code through API calls as opposed to just poking around arbitrarily. And research has shown how you can wrap whole operating systems and runtimes in these containers. You can wrap software containers like Docker containers in these containers, all the way down to low-level code objects that talk through, say, POSIX thread APIs. All right, so the rest of the slide is, rest of part 1 is going to be a potpourri of several other interesting hardware techniques that have interesting security applications. So the first is Intel TSX, which is Intel support for hardware transactional memory. You might think, well, what does this have to do with security? So in transactional memory, you can execute a blob of code, quote, atomically, so that either everything commits at the end atomically or it aborts. And this is interesting from a security perspective because as this code is executing, certain exceptions like page faults get suppressed until sometime later, say the end of the transaction. So going back to the previous slide, code can leak secrets depending on when exceptions happen. If you have a hardware mechanism to suppress those exceptions, that's a good thing. Second, there's Intel CAT, or cache allocation technology. So this was originally envisioned as a performance mechanism. You want to be able to isolate ways in your cache for a particular application so that it does not get contention from other applications. But not surprisingly, you can also use it to protect against cache side channels. And based on what Mo had said yesterday, you can also use it to abuse rowhammer. But there are pros and cons to most of these. I would say the pro is first and foremost. And then finally, this technique is kind of off to the side. It's not related to side channels per se, but it's still really interesting. There's this Intel extension called ptrace, which as an application runs, logs information about that application, its control flow and things like this. And researchers have shown recently how you can run ptrace concurrently with an application and dynamically, as the application is running, check to make sure that its control flows follow certain rules. So this is called control flow integrity. And then related to control flow integrity, I'll just give an obligatory call out to a rich literature in code instrumentation. A good exemplar of this is Google's NACL system, which allows you to instrument code so that it cannot break out of software sandboxes and is more resilient to code injection attacks. All right, so that was part one. Let's do part two. Part two is a general technique called data oblivious execution, which can stop side channels at different levels of abstraction. And the idea is that we can block side channels by statically scheduling program observable behaviors. So what do I mean by that? So one example is if I want to stop microarchitectural side channels, I can rewrite sensitive code like this. So this is also called constant time code. I think it's been covered in some talks already. The idea is if you want to hide whether a secret bit is a 1 or a 0, and that secret bit takes a conditional and causes some subsequent program behavior to change, you can blast that conditional into straight line code, essentially doing the work of both branches and then muxing at the end with a ternary operator. There's actually a bug in this code. I was meaning to put y is equal to 2 or something else like that to indicate that the memory access actually does leak whether the branch was taken. However, for the hardcore people in the audience, they'll tell me that even if y is equal to 1, they'll still be able to grab the bit. Okay, and what's really interesting about data oblivious execution is that it works at other levels as well. So you can also apply the same idea to block software API side channels. The idea is essentially the same. You want to block this secret conditional. Inside the conditional, you do a system call. So the solution is always do the system call and pad the arguments to hide what the argument actually is. So the programs that we end up getting are kind of static control flow graph-like programs where we have blobs of code that will always interact with their neighbors no matter what the conditions are. And I'll just stop this slide by saying that there's a lot of interesting domain-specific work in the space to speed up data oblivious code in machine learning or in database setting and other settings as well. And finally, the data oblivious code is not always slow. So oftentimes, you only have to treat a little bit of your program with this level of protection. And in some cases, even large, complicated programs don't have expensive data oblivious transformations. So dense linear algebra is already naturally written in this form and does not incur large overheads if you need to get this level of security. All right, so let me just wrap up really quickly by talking about encrypted computation. This is the kick on this slide is that we're going to permit no server-side TCP. And there's two main techniques. The first technique is onion encryption. Onion encryption is two ideas. The first idea is we have a suite of encryption schemes that go from secure to functional. On the functional side, we can have homomorphic encryption that can do operations on ciphertexts. We have schemes that reveal order of underlying plain texts, so on and so forth. So that's idea one. And idea number two is that if we take a plain text and wrap it in layers of these encryption schemes, going from most functional, least secure to least functional, most secure, we can opportunistically, based on the operations that we need on the plain texts, unpeel the onions so that only the ciphertexts that we actually need to do computation on have to be revealed. So it's a way of like opportunistically getting security in a larger system, and it's been applied in database settings. And lastly, to just finish up, I just want to give out a call out to homomorphic encryption. Systems people typically will say, like back in 2010, 2011, oh, it has a billion X overhead, it'll never be practical. Homomorphic encryption has actually come a long way. The Gen 2 and the Gen 3 schemes are actually quite fast. I'll just stop by giving an exemplar benchmark. So recent work shows that you can run a 7-layer convolutional neural net with public filters. That's a strong assumption, however realistic in many settings, and you can do this in about 3 seconds on a realistic data set. And I'll just say that homomorphic encryption is good when you have parallel workloads, scalar multiplication and addition, and that you should check it out. And I think I'll conclude there, and citations are on the slide.
All right, good morning, everybody. So we'll talk about defending against information leakage from a computer architecture point of view. What I'll do is I'll start with some review of how I see the field, and then present a technique that we propose that I think is quite powerful. So in terms of, from the computer architecture point of view, there are multiple ways to, there is some covert and side channel attacks. One exploits the timing variance due to the interference on a shared architecture resource. Of course, many pipeline structures, for example, functional units, buffers, random number generations, VTB. Of course, there are caches, TLBs, network, main memory. So lots of problems there. People have talked here also about power, electromagnetic emanations, thermal, even accelerators these days. So how do we defend from an architecture point of view of these things? First, we can look at constant time hardware implementations. We can look at resource partitioning, very popular, runtime diversification, and detection. So I'll briefly go over this. So this would be the holy grail, which would be constant time hardware implementation. But the problem is that the way we design computer architectures, the philosophy is completely the opposite of this thing. So what we do is make the common case fast, which means the execution times are all varied. Caches are the perfect example of this. So I cannot find many examples of this. For example, I find the Intel's hardware accelerator instruction set for encryption. That's an example, but not many. Most of the examples have focused on resource partitioning. So here, we partition the resources, and examples are disabling SMTs, partition caches, partition the on-chip network usage, partition the DRAM accesses. The challenge here, from a computer architecture point of view, is how do we minimize performance degradation and resource underutilization? Another approach is runtime diversification. The idea here is to introduce noise to the interference or measurement operations that an attacker may perform. For example, people have proposed introducing noise to system clocks, randomize the address mapping, a very popular example, add noise to resource management. And this can certainly limit the effectiveness of attacks, but the challenge is it's difficult to guarantee a complete defense with low performance overhead. Another approach is detection and auditing. So here would be detecting the possible presence of covert or side channels, for example, based on the characterization of the cache access patterns that we are observing or other low-level features. Another example is to use record and replay, which is a technique I'm going to present next in a few minutes. Another one is to use signal processing or machine learning techniques. The challenge here is it's difficult to achieve high precision with this. So let me talk about record and replay. I'm going to skip these 2 slides here. So what's record and deterministic replay? At a high level, this is an architecture technique where you run a program, okay, parallel or sequential program, and the OS or hardware records all the non-deterministic events in a log. This could be inputs to the program, for example, things that the program reads, system calls, calls to clocks, interrupts, and so on. And then you store this in a log, and then you have a replay run in another machine, maybe on the fly or offline, and the system injects, the operating system or the hypervisor injects the recorded events at the correct times. And this enforces a complete deterministic execution of the program. Okay, so let's take a look at this. Suppose I have a program that is running, in fact, a virtual machine that is running on one platform. This is the recorded virtual machine on this side. And then in another machine, on the fly, I have replaying virtual machines that are going to replay this program potentially on the fly, okay, on a different machine. As the program runs, this hypervisor records all the non-deterministic events that occur in the program. For example, input, as I said, interleaving of accesses to shared memory in the case of a parallel program, into this log. And then on the recording machine, I have a checkpointing replayer that reads this log and re-executes the program completely deterministically and creates checkpoints. These are the checkpoints. And this we can accomplish approximately 50% slower than the recording machine, which is tolerable. And in fact, the recording machine will be idle many times, so we can do it on the fly at the same speed. But now look at this. So whenever we think that there is an alarm, something that is suspicious, we put an alarm here, and then when the replayer sees this alarm, it spawns an alarm replayer that starts from the most recent checkpoint and re-executes from there with a high degree of inspection. So it does it slow potentially with a lot of analysis, and it detects what the problem is. Now, what's the key here? The key here is that this does not need to be precise. So to be able to find all the attacks in a precise manner, I need very expensive hardware. Think about ROMs, okay, return-oriented programming. I can have a shadow hardware stack, or I can have very hardware-intensive solutions to detect all the possible alarms, right? But this is very expensive. With this approach, I can have cheaper hardware and have false positives. Why? Because I can have the replayer detect that this was a false positive. For example, the replayer can, in software, simulate an infinite return-oriented stack, okay, and figure out, oh, this was simply overflow. So, bottom line is that there are many effects that I would have to support to detect the exact attacks. For example, in the case of a return-oriented stack, I would have to worry about multi-threading, one thread messing up the stack of another one. I could have cases when the operating system puts stuff on the software stack and then returns without having a call. Or there is cases where I have overflow of the stack, or cases where I don't have perfectly nesting. All these things, if I want to support in hardware, it's very expensive. I'm going to support a subset of that and put false positive alarms, and this will detect it. So that's the high-level idea. We have used this for a couple of things, but the high-level idea is that we have robustness at relatively modest hardware. The replayer handles false positives and basically corner cases. And it restores robustness to a system with imprecise hardware. Another good thing is that it's flexible. New attacks will appear no matter what we do, and we're going to use the same hardware, well, maybe slightly modified hardware, but we can use new replayers. And we can use this also for executing auditing. And we have applied this to cache-based cover channel attacks and drop attacks. If I have a couple of minutes now, I'll finish with how I see the existing landscape. The problem from an architecture point of view is that if there is sharing, there is a potential attack. And our goal as architects is to avoid sharing that to introduce a lot of performance degradation. So we need to understand the performance versus security trade-off of everything that we put. Another thing is that hardware designers nowadays are very confused because we don't have, or they don't have, a consistent threat model. So we need to do that. And also we need a quantitative way to estimate how effective a solution is. Okay, so we can tell the hardware designers, let's do this, and these are the cases that you're going to cover, and these are the cases you're not going to cover. So what's going to happen? What's coming? I think that we're going to see a lot of cache-based side channel and covered channel attacks at the architecture level. We've seen a couple of very scary examples recently, but there'll be attacks on all sorts of types of caches, non-coherent caches, non-inclusive, accelerator caches, compiler managed local memories. We're going to see attacks that target high-level information, as some of the people have explained already, such as input events like keystrokes, screen taps, swipes. And what we need to do is we need to develop new techniques to defend against these attacks, always keeping in mind that we cannot ask the programmer to do a lot of work. So, for example, asking the program to identify all the critical parts of their program may not be reasonable, because the programmer doesn't know. Okay, so that's all the points I want to make. Thank you.
Thank you. Mark.
Hi, I'm Mark Morrison from Rambus. Thank you, Patrick and Guru, for inviting me here. I'm going to talk about Spectre and Meltdown, primarily focusing on the mitigations. We've already seen some interesting talks on what the attacks are. I'll give a brief reminder of it, but I'm going to spend more time on the mitigations. So as an overview, what is Spectre? Spectre is software side channel attack that leverages speculative execution. Because there's branch prediction in all modern processors, it affects them. It actually is a little bit difficult to exploit, and it affects mostly just-in-time environments and crypto. We can mitigate it, but it's actually kind of a very flexible attack, so it's going to be a game of whack-a-mole for a while, for probably a long time. Meltdown is an attack that allows you where you actually can access memory that you're not supposed to in a speculative manner. It affects the cache, and then even though you don't get the answer in the process, you can still do the cache attacks that we've seen for the past couple of days. There is a patch available. It's fairly straightforward, but it does have a performance impact. Here are the researchers involved. We've actually heard from Daniel and Yuval, who are here. The expert at Rambus is actually Mike Hamburg, and he was involved in some very early discussions of putting these, having these ideas worked out. And he was supposed to be here, but he's giving this talk at another place, so you got me instead. So if you have an easy question or you want to say how great the talk is, that's fine. If you have a hard question, I will take it and pass it along to Mike. So let me do a brief review of Spectre and Meltdown. We've talked about it before, so I'll be quick. There are three main variants here. Variant one is bounds check bypass. That's where you go and access the memory before you've actually checked the bounds. Another one is branch target injection, where you basically fool the predictor into using the wrong branch of a, well, I'll show you that. And and then there's Meltdown, which allows you to access memory that you should not have been allowed to. So let's look at the variant 2 first. Basically, you shouldn't allow your secrets to flow to the memory addresses, but CPUs will speculate sometimes, and when you go and you access memory and it goes into cache, they don't roll back the cache. And so the security of your code will depend on whether or not your branch predictor is accurate. So the variant 2 outline would be if I've got a vtable which calls various methods using the same vtable, you train the vtable to point to the method that you want to use, and then when your victim calls that method, they're actually trying to call a different method, but they call the method that you've trained it to use, and that accesses memory that it shouldn't have speculatively. So what are the mitigations here? The idea is to prevent speculation on these indirect branches. Google has a hack to fix it because the return instruction uses a different branch predictor. So what they do is you call a widget and then you change the return address on the stack. This causes a misprediction that you always mispredict, but you can control how it's going to mispredict rather than letting the attacker control how it's going to mispredict. But as it turns out that on the modern processors, their predictors are too clever, and Google's patch doesn't always work. So what we're going to need is for the microprocessor vendors to issue patches. So what we really need is to flush the predictors whenever you do a context switch. So, so that way you can't train the predictor for the use by the victim, and don't share predictors when you're hyperthreading. Variant 1 is Spectre on conditional branches. I think we've talked about this a lot. Basically, you go out, you try to access memory that you don't have permission for, and changes the cache state. You don't get it in your process, but you get it by the side channel on the cache. I'll just basically the difference between Spectre Variant 1 and Meltdown is that they're essentially the same attack, but Spectre's when you're doing it against virtual machines and just-in-time execution environments, and Spectre's more direct against the kernel. Okay, so what's the mitigation for Variant 1? So in the virtual things is basically fences. I think we talked a little bit about that, but essentially you try to enforce the order in which things happen by these fences. Intel has an LFence instruction for just-in-time bounds checking. AMD is probably similar. In ARM, the conditional moves can't be speculated, which is good, but in future ARM, they're going to introduce this flaw, so now they're going to have to use fences too. At least they're aware of it. And the performance here impact is pretty unclear on JIT. Variant 3, Meltdown, once again, now you're trying to access memory. It's the same attack. So the problem is that the CPU goes out and fetches memory before it does the bounds checking. Intel, Cortex, the ARM, and Apple processors are all vulnerable to this. Apparently not AMD. Like I said, I'm not going to spend too much time on stuff we've seen before. There's an interesting point on this slide, and which ties into the first talk by Chris. He pointed out that you could use the exception suppression as a way to mitigate side channel attacks. But in fact, you have to be really careful when you're doing these kinds of analysis, because you can actually use that suppression to improve the attack. So if you're doing a meltdown attack and you try to access memory that you don't have permission for, it will update the cache, then throw an exception. If you can suppress the exception, well, but when it throws an exception, then you have to handle the exception, then you got to restart the attack. It's a pain in the neck, right? It's going to slow the attack down. Well, what if I want to speed the attack up? Well, what I'll do is I'll begin the transaction, right? To access the kernel memory. I'll then abort the transaction. The cache won't be rolled back, but I won't have to deal with the exception anymore because I aborted the transaction and I never got the exception. So this is the difficulty that our community is facing. We're trying to come up with these approaches to mitigate the attacks, but it's actually very difficult to understand, because of the complexity of these processors, all the different effects that doing one thing versus another will have. So while suppressing the exception might help in some certain circumstances. In this case, in meltdown, it actually helps the attack. The meltdown mitigation is actually pretty straightforward. The problem is that the modern processors were using the same, or OSs were using the same page table with all the memory addresses for all the processes. And that's just done for performance reasons. So the fix here is that each process gets its own separate page table, and that you do throw a fault if you try to access the wrong memory. So future work. We're throwing around these attacks. They're actually not easy to exploit. I think one of the attacks yesterday talked about how trying to get a cache attack, even on a pristine environment, was a full, full year's work, or however long it took. So they are hard to exploit, but I think attacks always get better, so it's going to be possible. The question is, how hard are they to mitigate? And I think we're going to find that, especially with things like Spectre, we're going to be playing whack-a-mole for quite a long time. And even fix things that we think are fixed. We see this a lot in the attack community. You think you've put a fix, but your fix actually opens up a new door. So I think this is going to be kind of difficult. Do Spectre and Meltdown affect ARM Trust Zone? This might be a slightly older slide. Does anybody know? No? Okay, there's a research project for some of the students out there. And what other processors are vulnerable to these? So how do we prevent future attacks on the CPUs? Well, obviously, don't skip your security checks. That's an obvious one. The problem that we're going to run into is that we can't really get rid of speculative execution in general. It's just too important a tool. It just makes the processors much more efficient. So what can we do? Well, we can analyze the CPUs, their architectures, how they actually operate, and try to determine where leaks are going to be in these. This is going to be a lot of work. Can you design your CPUs so that you can easily write code in a way that it doesn't work? So what's going to happen here is you're going to have these code that runs slower. Perhaps we need the CPUs to enable a security mode, which is, okay, I am now working on security, on critical data. I want you to turn off all your fancy predictions and so on. But that's going to be difficult. It's also going to be difficult to analyze, and it's going to be difficult to keep efficient. Another option is to run in secure enclave. So basically have a security coprocessor perhaps that is your root of trust, holds the keys, you do the crypto there. It's going to be simpler, it's going to have fewer features, it's not going to be fancy or as fast, but you will be able to do your analysis of the risk much better on a much simpler processor. So I think there's a lot of work to be done in this. And that's all I have.
So thank you for the interesting talks. I think you'll enjoy listening to you.
I have two questions, one for the first speaker, one for the third speaker. You mentioned TSX, CAT, and ptrace. Are you aware of any ARM counterparts for those?
That's a good question. Off the top of my head, no, but I can look and send to the organizers afterwards.
For the Spectre and Meltdown, how difficult would it be to, once we do speculative execution and we realize it was wrong, make that cache write-only, or just like...
Or roll it back, or...
Yeah, so that looks like the straightforward.
It looks straightforward. It also
yeah.
sounds expensive,
Yeah.
like because somehow you have to keep some extra cache around so that you can roll back the cache that you just updated. So it might be doable, but I think it's going to be expensive.
You have to remove all the side effects, all and everything, including replacement changes, right? The state of the replacement algorithm, everything.
So it's a question for Josep and kind of let's let things execute, let's kind of monitor them loosely and then have a replay. How do you envision the replay happening? I mean, if it happens on the same machine, essentially what you're doing for the other side channel attack is essentially a kind of slow motion, thing. So basically, I mean, normally attacks need a lot of bandwidth for some of these, like EM and so on. And if things are done in slow motion because you're doing analysis, that's actually gonna really help. So for example, I can now see individual bits because you're so slow.
Okay, first thing, this is a high-level primitive. We're still refining how it's going to work, right? Second, we think that we can do this at the same speed. So the attacker wouldn't notice that the machine is slowed down in any way. Third, we would want to have this replay in a different machine that is very secure. So you cannot attack that machine, if that's what you're asking.
The real question is basically if this replay is done with a lot of analysis, it's going to be kind of stretched out, so you can do much more detailed analysis of that from the side channel.
Okay, but so remember, the analysis occurs in parallel, right? And you may have 3 or 4 replayers going on at the same time. Replay processes, each of them checking one alarm, a different alarm, or different levels of analysis for the same alarm. Sorry.
Yeah, I have a question for Josep. To follow up on Miloš's question, so looking at this from an attacker's perspective, I'm going to hit every single alarm to make this thing run as slow as I can get it to run, only for it to leak more, because the slower something runs, the more it leaks, and you're now introducing even more analytics code that touches the data even more. So for me, I want all of them to hit. I want all possible alarms, and then I'm going to see the leakage from your analytics code.
Okay, so just to repeat what I said before, the processing of an alarm happens in a different machine, right? The original program continues to run, and then on the replay machine, for each alarm, we spawn a new replayer that happens in parallel. So at any point in time, you may have multiple replayers going on. The replayer, not the checkpointing replayer, the alarm replayer is very slow, as you say, but you may have multiple of them.
Why multiples doesn't stop side channels? Multiples just annoy attackers. I mean, the fact that you have multiple replayers means more data, not less data. As far as I see it.
Okay, so I think what you're worried about is for me to slow down the original execution. Is that correct?
No, I'm worried about you having an additional execution that handles the same data, that runs slower, which is now a more lucrative target just because.
Oh, but this machine is hidden in some other place. Nobody can touch
I
this
see,
machine.
okay.
That's the assumption is that this is a secure machine.
So I have a question, and I'm going to use the example that Chris mentioned in his slides, but it's a general question for all the 3 speakers. So we talk about, at software level, how we can, in some sense, avoid this kind of poor, branch based on secret. And Chris used this example of, fetch both memory content and then use a mux to do that. So the first question is, so what happens if your compiler, when doing optimization, just, reverse this? And we have seen this from hardware design, because I come from hardware background. If you write your Verilog code similar to this, and then the compiler with the synthesizer will probably just go back, change it to an if statement. So in that case, once you run your real executable, it becomes the same thing. And then the second question will be if you come down to the hardware level. So you mentioned about the function called mux, and how mux is implemented. Because mux, again, it is a comparison. So in that case, if you go down to the hardware, it is still an if statement. Your secret is still there, and then you can still leak set channel information. In that sense, the mitigation from software may not work. So that is my question. So first, how do you go from software level past the optimization phase in compiler, and then how do you collaborate with the hardware implementation? Thank you.
Yeah, so this is a really good point, and I think the short answer is that you're totally right on both counts. Constant time code and data oblivious code works in theory. However, if the compiler undermines you, that's a problem, and God forbid the hardware undermines you. So the MUX, I didn't give an implementation of it. People can implement it using low-level bitwise operations, or in some case C moves. In the case of a C move, I think another speaker mentioned, well, what if they microcode it into a branch and a move? And we start speculating on that branch. Well, then that completely undermines the protection. So as of today, we don't have hardware support for data oblivious execution. That's a big problem. And as of today, we also do not have a guarantee from the compiler side. Although I will say that people who write data oblivious code, they usually work at they work at the level of wrapper functions, so they'll wrap the low-level primitives like a CMove plus maybe some auxiliary instructions, maybe a fence in the worst case, that will try to protect the CMove, but there's still no guarantees ultimately. So they'll do things to make the compiler's job harder, but, and I think another speaker mentioned this, if your compiler level branch predictor, so to speak, is too clever and it goes into those low-level functions and it tries to rewrite them, then you're in trouble.
Because we did this for very long. It just did exactly the same thing. Just remove this memory too.
Yep.
Right, and even if you try to fix it in the software, right now the modern processors are so complex, and it's very difficult for somebody writing software to understand, even at the assembly level, what the processor is going to do and in what order it's going to process the instructions. They have the pipelines and they do the out of order instruction. So even though you think you've got, say, like your LFENCE, to protect against variant 1 set up correctly, because of the way the processor in its, basically its little black box is doing what it does, your LFENCE may not work to protect the Spectre attacks. So it's more than just writing the software well. You have to really begin to understand how the hardware is going to execute, and I think realistically most programmers are not going to understand at that level. So it's going to be a very difficult problem overall.
So while the next set of speakers set up, I have a quick question for Chris. You brought up this COTS, right? I'm a big fan of COTS myself. So how can you, when we argue for, okay, let's use this hardware with a little bit of signal processing to mitigate something, the usual complaint that I get is like, wait a minute, you cannot comprehensively, close everything. So there is this, COTS cannot guarantee things, but it can provide you the best effort. So where do you see this, this gap, how do you see this gap, closing the gap between the two?
Yeah, so in the 3 parts of my talk, I intended for it to be a spectrum. On the first slide, you talk about like Intel CAT, TSX. These are kind of like blunt hammers for doing a very specific job that has been brought up by other speakers. They can usually also be exploited for different attacks, and they don't give holistic protection, really. And then the next technique, data oblivious execution, really strives for a holistic defense. It just has some key problems, as someone just asked a question about compilers and the low hardware. And then the third is encrypted computation, where I don't care what your hardware is doing, what your CMOVs are doing, if you use cryptography, and I think the real free lunch nowadays is that cryptography can do a lot more than simply encrypt and decrypt. So there actually is, and reasonably efficiently, so there actually is a path forward if you really don't trust anything about the hardware. But in terms of closing this gap, I think a really reasonable question to ask is, on the spectrum of trusted computing-based size, going from 0 to trusting everything, including the operating system, what is the efficiency overhead of that scheme? Where is the kink? So there's a kink clearly when you go to data oblivious execution, because you're doing a lot of extra work, but you're not invoking cryptography. And then if you want to go from just trusting the hardware to trusting nothing, then you skyrocket up another 1000x or whatever it is to pay the price of encrypted computation. So I think we should look at this in that 2-dimensional spectrum, and where the sweet spot is depends on the application.
Let's thank the speakers again. So we'll move on to the third plenary. It's about new computing paradigms to mitigate information leakage. We have three great speakers, Inchan, Carlos, and Ro. So let's get started.
Thank you very much for the introduction. I'm Inchan Zhang from Ohio State. Well, I come from the system security community, and I've been working on side channels from the system perspective for almost 8 years. But to be very clear, the type of side channel I work on is like two computations sharing the same computer system, and primarily on the microarchitecture level, the share of CPU caches, branch prediction units, or translation loops and buffers. Well, please indulge me to digress a little bit because I know this workshop is about microarchitecture side channels, but I also want to point out that since we are considering system level defenses, we have to think about some system level side channels as well. And examples of this system level side channels include some operating system statistics like the profile systems in Linux, or the resource access pattern, like one of the famous example is that the memory page access pattern from the SGS enclave code that can leak information about what is inside enclave. And also the file system access pattern of the searchable in symmetric encryption systems, or even the timing channel created by shared kernel data structure. These are system level side channels. But although I'm going to focus on microarchitecture side channels, but my point here is that the side channel is very broad in concept. And if we think about them carefully, they share some common solutions. And what exactly are these solutions? I'm going to give a taxonomy of system level side channel defense ideas. So basically, I consider there are 5 different ideas to implement the side channel defense in the system level. One such idea is resource partition. So for instance, we can partition resource from the spatial perspective or temporal perspective. Spatial partition, one example is that we can partition the lateral cache that is shared by multiple computations in terms of cache sets or cache lines. And temporal partition, well, here I mean one example is to partition the time shared private cache. When there is context switch, you simply cleanse the entire shared private cache, so there is no temporal sharing between computations. Another idea of system level side channel defense is to restrict the timer. So this may happen in the public cloud computation or even in web browsers, where the attacker can be a hosted virtual machine or a sandbox JavaScript. And in these scenarios, the cloud provider or the browser designer may restrict the timer that is accessible to this malicious code. And there are 2 ways to restrict the timer. One is by using the fuzzy timer to make the timer less accurate, and the other is to make the execution deterministic with respect to the different inputs. Well, another idea is to inject noise into the system, into the side channel. Again, there are 2 different ways to inject noise. One is to inject noise directly into the side channel, such as we can make the profile system in the Linux operating system, the reading is not accurate. Well, that is one idea. Another idea is directly access cache, so that the cache observation is more noisy. This is the first category of injecting noise. The second category is to inject noise into the execution itself. For instance, we can introduce decoy execution or diversified execution or randomized address-based layout. These are, in my opinion, can all be categorized into this noise injection category. Well, a fourth category, in my opinion, is to detect the attack at runtime. Well, again, there are 2 different ways to do that. One is that if you're implementing this intrusion attack detection in the system level, one idea is that you can use performance counters, the hardware performance counters, to monitor the use of the CPU hardware to detect whether there are side channels or core channels at runtime. And another idea is to detect by the software itself, which will involve program instrumentation. I will talk about this idea a little more later. Okay. The last, the last category of defense from the system perspective is to eliminate vulnerability. That is, well, a no-brainer. So there have been quite a bit of work to identify the secret dependent as pattern or system statistics that may lead to leak information, and also there are work of eliminating these vulnerabilities. Well, I've been fortunate to have been working on this direction for many years, and I think my previous work have been involved in most of these categories. But today I cannot cover all of them. But I want to highlight two interesting ideas that we have been exploring recently. The two ideas. One of the ideas is to embed side-channel attack detection capabilities into the program execution itself. Okay, and the second idea is injecting noise into the program execution with statistical privacy guarantees. Well, let me talk about the first idea first. Well, we started exploring this idea like almost seven years ago. Back then, back then the study of side-channel attacks in public and multi-tenant clouds were very popular. And back then, we were trying to convince the cloud provider to implement some defense into the cloud hypervisor, but it was very difficult. And still, it is difficult right now. But just the solution we thought about was trying to embed some attack detection capability into the guest VM itself. So that will allow the guest VM to find some way to detect whether there are attacks against them. Actually, we have two publications along this line. One of these was a Oakland 11 paper, which is called Homegrown. And the idea of that paper is to proactively monitor the shared use of lots of cache, so to find who else is running on the shared cache. And in this way, we can somehow detect some abnormal activities from the other third-party VMs. And another paper in which we explored this detection idea was called DUPO, which was a CCS 13 paper. And the idea was similar. We also modified the operating system kernel, but the idea here is to detect frequent context switch. And because frequent context switch means there might be a L1 level, L1 cache side-channel attack that was going on. But it is worth noting that in both these approaches, we are not assuming a malicious cloud provider. We are assuming the cloud provider is not collaborating, but still benign. But recently, we applied this idea to, this embedding attack detection capability idea in the context of Intel SGX. Now the scenario, the threat model is different. In the threat model of Intel SGX, the operating system is not trusted. So it is possible for the malicious operating system to perform side-channel attacks. And now there is no system-level defense. So what we did is to come up with some compiler-assist approach to automatically instrument the enclave program, so that at runtime, the enclave program will run and frequently trigger some detection logic, so we can detect whether there are side-channel attacks or not at runtime. That's the high-level idea. And we use it. We explore this idea again in two different papers. One of the paper is a very recent Oakland 18 paper, which will be presented in 2 months. The title of the paper is called "Racing into Hyperspace: Closing Hyper-Threading Side Channels on SGX with Contracted Databases." I just briefly introduced the high-level idea of this paper. So the purpose of this tool is to guarantee that when the SGX enclave code is running, nobody else, no malicious code is also running on the sibling hyperthread. Okay, that is the goal. And we are using a pure software solution to achieve this goal. By instrumenting the program and by instrumenting the program and detecting this physical core collocation at runtime. I'll skip the detail. If you're interested, you can go to Auckland and we can talk about this in more details. Another paper is a similar idea that we published in CCS to detect frequent asynchronous enclave exit, which is also another trend for side channel attacks. Well, another concept I want to briefly introduce is execution privacy, which is a term coined by myself and Professor Mike Reiter at UNC Chapel Hill. Well, we use this execution privacy framework to guide noise injection to mitigate side channels. Okay, this is injecting noise to mitigate side channels is a very ad hoc idea. How much noise can we inject into the system to provably eliminate side channels? That is a question that we want to answer with this execution privacy framework. And the idea is very simple, that we try to model side channel attacks as a sequence of observations and somehow devise a randomized mechanism so that we can inject noise that can achieve a differentially private observation sequence. That's a high-level idea. And again, we have applied this idea in two different scenarios. One is the profile system in Linux, and the other is the symmetric searchable encryption. And these are two recent papers. And we are still exploring how to apply this idea to defeat microarchitecture side channels, which is much harder, but it's still work ongoing. Well, I'll wrap up here. These are a list of related work. Many, I think if you're, I don't think this list is very comprehensive. If your work is not here, please let me know. I'll add it into the references. Thank you very much.
Good morning, everybody. I'm Carlos Rosas from Intel Labs. We'll be talking about sort of mitigation approaches, but mainly it's going to be a call to action to you as to what, from an industry lab researcher, we need academia to do. And you can tell that my corporate folks did this. So this is an educational aspect. I do not represent really Intel product. I'm a researcher at Intel, so I'm on the fence. What I've done. I'm an Intel software guard extensions architect, so I am crazy, if you talk to the product guys, to get something that innovated in. So if you guys have questions, I'm free to answer any questions you have around there. More generally, I run a research team that's looking at protecting data and computation in the cloud. So beyond SGX, we do a lot of work on use cases, and of course, side channels now has become very relevant to us. So I want to, I know we've done sort of bounds checks and the spectral variations. And I want to run this through, but just sort of talk a little bit about the attack and the mitigation, and talk maybe a little bit one of the people who are missing here are sort of really the managed runtime folks, right? I think have to in this community sort of get more of the software folks involved in here, because it is going to be a software hardware co-design discussion, right? It's not just going to be us architects or the designers, but we really need to get those level of people inside and into this community and this conversation itself. So in this particular system, we've already seen it. We have some data here. We have some secure data, which is unfortunately placed next to this data array, which we're going to overflow. We have set up our system so that we can prime the leakage back from this array 2, which is going to be our leakage element coming out. And then we have sort of set up the offset here to as an input to purposely trigger here. We've probably done some work to move the array length out because we want to open up the speculation window, which on Intel processors on the latest generation is about 200 instructions. So you can do actually a lot of work before the window closes on you. So we have set up the length array so that we've had to go all the way out to main memory, which can be about 200 clocks if you want to sit around there. And we go ahead and overflow. So we've read some secret here in the cache. And then we've gone ahead and read this index, which we cleared out before. So we're going to do some sort of priming probe here. and we'll time back. And of course, what's going to happen is eventually the processor catches up and says, oops, I incorrectly predicted the answer here, and I'm going to go ahead and go off, and now I've leaked the secret. So what do we do? So the sort of current architectural advice is to fence off the operation. Right, we're going to put an L fence in here, and essentially it'll just stop the speculation. So even though there's a miss, the processor just waits and waits and waits, and then, you know, it will sort of resolve the branch correctly. What's the problem? It's a performance cost, right? And this performance cost in one of two ways you look at it. We either pessimistically induce the L fences, right, in which you can get upwards to 40% performance costs if you take like a SHA routine and pessimistically insert. Alternatively, you sort of take best guesses on statics, but then we have sort of unknown security properties, right? And in fact, I don't think you can actually close it statically. I think there is actually enough dynamic information flow that is sort of an open problem right now as to how do you actually do this without sort of going all the way to pessimistic, without a well-defined sort of model of what to do, both at the software level, because the compiler may not know this is security critical, right? So which ones do you do? So this was my favorite one actually, right? Because there's Dimitri here or not. I thought a lot of the interesting work was manipulating this branch predictor, right? Which is really this notion that hey, we have this stack there, and people might have done a really good job of protecting the stack in terms of corruptions, but there's this other piece of state that the processor had that was essentially open to manipulation, right? And as a community, we had sort of these indicators here of manipulation possible, extracting information out. And in this particular case, we've trained the predictors, and Dimitri can tell you can train the directional predictors as well. And so same sort of thing happens, right? We have some jump that we want to go, but we went ahead to the gadget instead. The gadget goes and does the same leaks, and same thing occurred. So what do we do here? So someone talked about sort of the ret Pauline operation, which if you haven't looked at it, it's a nice piece of engineering. The amount of work and the elegance that went into that solution is amazing. As he talked about, processor guys are too clever. There are processors in the pipeline that will break it. So what do we do instead? What Intel ended up doing is sort of introducing a bunch of new ways of sort of controlling the branch predictor itself. So one basically allows you to go ahead and clear the branch predictor. Another one basically says separate the branch prediction across the siblings, right? And another one sort of a barrier perspective, right? And so the fundamental idea is that you insert this sort of predictor from whatever your transition is from one security context to the next, right? We just go ahead and clear the branch predictor. And by clearing the branch predictor now, the adversary is unable to sort of make us force to make the ROP gadget work essentially, and then we're done. So again, there are some other nice things coming down the pipeline when we look at it. So CET, we were able to intercept that. You won't speculate past that check. So someone talked about how have the processor speculate past your security checks. Yes, absolutely. And this sort of gets to the next thing, right? We have to sort of differentiate security checks from other checks, right, into the ISA and whatnot, so that we can actually train the system to know these things. So I want to talk about caches a little bit. I think we've talked a lot about it. The community's done a really good job, I thought, of sort of driving some of the research in terms of slowing down side channel bandwidth we have today. Started partition, we talked about cat, and there's cat and core, cat and atom. There's things going on there gets better. The randomization-based defenses are really nice, kind of scary when you look to implement them. But now I think we can actually maybe drive some more research in that space and try to evaluate these things. I'm not saying that any product team will do them, but they're at least willing to listen now, which is a huge step forward. But I think the whole research question now is, what could we do with speculative updates? You know, it's not a very clear. I know someone said it conceptually sounds easy, but I think you know, as computer architects, we know this is a non-trivial problem, right? You're fundamentally trying to change the coherence protocols in the system, right? So this would be a fairly radical change. And then, how effective would it be, right? Is this worth doing? Is an interesting question. So I'm expecting Yoav and Daniel there to tell me, like, well, look, there's 5 other covert channels that are just as good. We just don't use them because they're a little harder to use. You know, the impact of performance is not really quantitative. We don't know yet. And then I mentioned already sort of complexity, right? And so this really bounds back to, I think we've done some work. I know Princeton did some work on sort of looking at these caches and sort of quantifying the performance and benefits of these. We need more work in that space, right? Especially as these evolving attack models occurs, we need more of that data. So if we sort of summarize, current mitigations can be expensive, right? The granularity, we're driving to more fine grain. If we look at the software trend, especially in the server land, we went to VMs, to containers, to functions, right? So as we look at these sorts of sandboxings and whatnots, we need the protection mechanisms to scale. We just don't have enough ways in the cache, especially when you try to nest these things in capabilities. You have a VM you want to protect, the VM has a container inside you want to protect, and that container inside has a function. Now what, right? What's the sort of interface allows us to sort of have the scalable and secure performance. The security attack, they're evolving. You know, you guys are researching, it's really great. We see the things coming in as people explore all the different things. Someone off on the formal side, we sort of need to get down to those next levels of sort of formalizations in there. So as we go to evaluate, and we've talked about, we fix one problem, we don't cause another one. And this leads me to the call to action to you. All right, as the community of architects, what is the right way to expose speculation? I know some folks seem pessimistic, but I think there's an avenue here. Just like we went through memory ordering and specifying that, I think there's an avenue to getting there. Once we sort of get to that, what's the right way to solve the problem? Is it new abstractions, sandboxing, so we can declare what security checks are? Just new directives for constraining speculation like we do for memory. Constraining information flow. Let's not worry about how we constrain speculation, but where it can go in terms of data flow, right? To tooling people, we're going to have lots of questions, right? How do we know that we've characterized well what the microarchitecture side channels are? Where are they? And really, I'm going to call to you as a community to help provide the answers, because my team's not big enough to answer all these questions. All right, thank you.
Hi. So I'm Ro, my affiliation is Qualcomm Technologies, and I'm more specifically part of Qualcomm Research based in San Diego. And besides other things that they do, oh, I see. And besides many other things that they do, there are really 2 heads in my portion of technical work. One, I do computer architecture. The other part, I do computer security, and specifically applied cryptography. And so this community at this time is never more appropriate to look into problems that are at the intersection between computer security and computer architecture. And also to look into such a problem that go beyond just cryptography. And before I really start, because I want to So moving into applied cryptography is kind of interesting because it was a completely new world for me. So I wanted to share part of the story with you, and also to share the lesson learned when you start from the traditional type of side channel that has been primarily developed in the landscape of smart card, and you move it to SoC. So what happens to cryptography attack and mitigations? And on the other hand, we are going to extend it beyond cryptography, which is all these attacks that we are seeing recently happening, But my perspective is still the perspective of someone that works for a company that pull out the products that are sold in the consumer electronics. So what this means, it means that the life cycle of these products is very, very quick in some use cases, but then there are also emerging use cases that look at products that have a much larger lifespan and so require a different type of attention when you look into such kind of problems. So one of the first tasks that I was charged with when I started my side channel research was really to say, you know, our mobile phones or our mobile devices in general will start running premium contents like video, movies. And you know, the first threat that you have to movies is privacy. And therefore your digital right management embodiment that you put into the phone will use cryptography that is usually required in the traditional DRM protection schemes to have side channel protection to your cryptographic implementations, both software and hardware. Now, an SoC has billions of transistors into it, and we were looking at protecting something that runs in 10 cycles. 10 cycles, really. An AES optimized in hardware runs, the best it can run is 10 cycles. So I started looking at the problem, I went back to product management, and you know, I said, you know what, we don't have mitigations. So if you look at the theorization of differential analysis, it means that asymptotically, if you collect an arbitrarily large number of traces, and you probe nearly, not even in the right point, in proximity, you actually will be able to extract the key. Then you go back to our product team, and they say, no, it's too complex. There is no way you are going to get anything out of that. And because they were comparing the SoC to the smart cards. So if we look at traditional recipes for side channel attacks, so you have this recording device, and I'm talking about probing. When we move to microarchitecture, things are slightly different, but in terms of results, and if you compare to what the certification tells you, it's pretty much the same. The attack changes in complexity in terms of the signal processing that you do, but they are pretty much the same, and they are very effective. And if you would put them to the same compliance that smart cards needs to pass in order to operate in the market, well, system on chip will fail compliance anyway, in spite of their complexity. And so you have these recording devices, and you need to have some form of physical access. No, that's not true. You need to have some physical proximity. And you have different type of side channel that serves as proxy between the secret information that is usually targeted or traditionally targeted for this type of attacks, and basically the actual execution. You do a lot of information processing, and the goal for the traditional side channel is actually key extraction. You want to break the secret that protects the valuable data, and then start basically doing your own business through fraud, piracy, and etc. The point here is that in this space, the attacker is also moved by a single motivation, which is profit. And it's profit meaning that I want to make a few $1 million with something that requires me time and equipment that is in the order of a few $1,000s. And the difference between one attack being effective versus another attack being effective sometimes is the experience of the attacker, oftentimes it's the technology factor in the setup that the attacker can have access to. But the point is, being all this literature developed within the smart card sectors, where you are actually protecting secrets that protect money or related to money, there is a very strong regulation. So metrics, procedures, and processes that allow you to go to a third-party evaluation lab and say, this is my cryptographic implementation. You don't even give the whole system. You actually give your cryptographic implementation. They know how to poke into it. Actually, that's not true. You tell them how to poke into it, and they run basically an attack that is completely well engineered. To some extent, I remember talking to someone, Then she said, oh, you know what, I just plug this thing in, I press a button, and the leakage test tells me, oh, this is good, this is bad. So if we move all of these, moving forward, basically to a modern SOC, definitively you can attack cryptography. But the problem is that there are many more goals that an attackers try to achieve. Like, for example, software fingerprinting. So the type of attacks that you have differently from the type of attack vector that you can enable by looking at the microarchitectural side channel attacks may involve the first few steps to, for example, enable buffer overflow where your software is actually written with the best coding practices for security. And here really I'm not talking of side channel attacks, I'm talking more of injecting faults. And here we have Patrick, who is probably, is probably the first person that pioneered injecting fault into modern pipelines. So pipelines are relatively complex, and people would say, okay, can you actually really do something? And I remember at some point at FDTC in 2014, there was some industry presentation saying, we tried to inject a fault at this stage of the pipeline, and the processor crashed. So basically the fault is pretty much useless. Then Patrick the next year started saying, oh, we can skip instruction if you craft your fault properly, and we can make a control flow diversion and things like that. So his work has been adopted by one of the certification labs that now have more sophisticated attack tools. But the point here is that in addition to the traditional methods of attacking devices, in modern microprocessor, you also have a covert side channel that are something different. It's like going from the physical world to an abstraction that you can create, which is the covert side channel. And on the other end, there is this other thing that attacks are much more sophisticated in the sense of what they can achieve, because they can run within the same address space across different address spaces. And the point is that they don't require any form of proximity. So if someone is doing a side channel attack, or it has an antenna right behind the door and trying to hack my computer, I might see this person with this antenna, and it's suspicious to me. But all these attacks are completely stealth. And the problem with their stealthiness is that no one is going to report to our product security team that last year there has been 10 or hundreds of incidents that are related to side channel attacks. You actually do not know. And this is a major problem in industry for a product team to basically take actions. So one thing that I would say is that as the evaluation is very well specified within the traditional cryptography, when you move basically to modern SOC, really the testing and certification paths are to be paved, and that's a major problem within industry. But also, with the SOC, there is also a technology problem, that technology is shrinking. And the number of countermeasures that you need to deploy, both for traditional cryptography, needs to bubble up in the stack. So at the microarchitecture level, the memory hierarchy needs to be probably all re-architected, and up to the compiler. So we have done some work that try to leverage vectorization as mitigation against fault attacks, and also value prediction against fault attacks. So one of the things is that within the microprocessor there are so many things architected that oftentimes it's good for us to look in what exists and learn from both communities. So in general, it's not always the right thing to fix a security problem. Because it's continuously a rat race that once you have been fixing one problem, another problem opens and opens and opens and opens. And in the end, at the end of the day, you have a system with so many mitigations and you don't even know how they interact with each other. So the incident response needs to be done in a sense. And in addition to that, really side channels are unclear because you don't know exactly when incidents are related to side channel until there is something really, really big like Spectre and Meltdown. But we can see that we need to look into this problem because of a number of trends that are happening. So general purpose processors are becoming ubiquitous. And this is true really from server side down to some class of IoT. So therefore, anything that is applicable to a complex SoC is going to be applicable all over the place. The value of the content is increasing, pretty much like in the credit card. Now we have valuable content processed everywhere, and therefore physical attacks or any form of them is going to be important. Microarchitecture covert channel, we are seeing them very often. Many of these attacks are actually not very well engineered, but if we look, for example, at the literature that look at the memory hierarchy type of attack, I think it's pretty mature to the point that we could get together and start looking into compliance testing. What does it mean for a cache to be resistant, and what are the mitigations? So we have seen in the previous presentation the RP cache. The RP cache is a beautiful concept that tries to randomize the set allocation policies. And the channel that basically, the communication channel that basically through which usually caches leak, the RP cache actually is probably, can be proven to not leak information. So it's a channel with zero capacity. And it's very interesting. But then but it's difficult to implement. But then at that point, if we have other solutions that can mitigate to some extent, so how do we evaluate them in terms of certification? So is it required? And actually, at the moment, it's not required yet. And therefore, while academia continue to work together, I invite the computer architecture community to work with the security community. An example is what is happening at Northeastern University with Yunsi Fei and David Kali. So we need more of that. We need to cross-educate each other to the various problems. And at the same time, the industry would start to get together and putting some sort of guidelines, certifications, and rules, at least for the attacks that are engineered. And for the academics, last but not least, try to look into things that go beyond the proof of concept, because that is what actually help industry to be more confident into start looking into adoption. See?
So let's invite the speakers.
I think the part of least resistance here.
I have a question for Carlos. So I looked at your slides. So you talk about software abstractions and software directives. Really the problem, this is a hardware problem. I'm talking about the Spectre solution, how to solve the problem. I don't think that with software abstractions or directives you're going to solve the problem. How willing is Intel to actually redesign the processor? Because that's what you really need. Get down to hardware changes. That's one question. The second is, I liked your last bullet, which is a call of action for academia to do research. Now, we need some funds from Intel. How willing is Intel to provide some funds? Because there's lots of interesting, intelligent people here who could use those funds.
This is interesting.
So I agree that software will not be able to solve this by themselves. I don't think hardware will solve it by themselves either. I absolutely don't. I mean, we don't solve memory concurrency in hardware alone, right? Software algorithms have to understand the memory ordering to accomplish that. So the call really was to say that I think we do need to sort of put some of these things at a first order, figure out ways of documenting in ways that don't hand time the implementation excessively, but give software enough so that they can craft solutions. And I think we've talked about this in the whole community that I don't think anyone believes that there's a single layer that will solve this problem by themselves. I guess the second item, we've done some funding. I expect we'll have some additional funding. So if you have really great ideas, come talk to me. If you have really good students, come talk to me.
Yeah, and I want to follow up in terms of possibility of funding. So as Carlos pointed out, so usually we do direct funding to industries and problem. I can give you the example of the vectorization approach that I was talking about, as well as the branch predictors and other things, the value predictor and other things. Actually, it's interesting to start working to things like value prediction, that it's not, there is no processor that claim to have it, but it's very likely, in my opinion, the next generation of processor are going to have that. So we can start working on problems that are known now, and once we architect and put into it. So, and we work with academia in order to do that. Other forms of fundings come through industry organizations. So one of the other hats that I have, in addition to university relations, is standards and industry organization. So the Semiconductor Research Corporation is an excellent venue. So perhaps the grants are not that big. I understand for some of you. But it's a very interesting venue to gather together requirements and funding that are channeled through the corporation to academia. And in the security space, the Semiconductor Research Corporation is the T3S ability, which before started from microelectronics security, but now it's going up to microarchitecture and whatever. Another opportunity, and that was something that Dave Calley was telling yesterday, this new form of starting off research centers that are heavily industry driven in terms of requirement. It seems that in this space there is a huge need for industry drivers for setting up a specification pretty much in the same way as in traditional side channel attacks and defenses have been doing in the smart card domain. But for problems that are not necessarily as well defined. So key extraction is a well-defined problem. Software fingerprinting is a well-defined problem, because if you came across a virtual machine, fingerprint the software and say, oh, you know that the virtual machine collocated with me as this version of libjpeg that suffers of this and that buffer overflow, and you obtain the information through a side channel, then those type of problems one can start to gather together and also drive, because they are very concrete. So there are several forms that I think. Yeah. Just talk to us. Yes.
Kind of on a related note, I mean, from what I see, basically many of these modern attacks are kind of like composable, as in you compose several things and they work together kind of for an end-to-end attack. And I'm just there is this kind of tug of war almost between as a researcher, how much do I need to construct an end-to-end attack, and how much do I need to just demonstrate that there is a component that can be plugged into pretty much like 5 or 6 existing attacks as a replacement for something else. I mean, case in point, for example, when you, in spectral meltdown, when you say, okay, I can prevent the leakage through the cache, and thus, yeah, you can do speculation, but it doesn't leak because I'm not doing speculative cache accesses. You will fetch instructions speculatively, so I can just convert my attack into, okay, now I'm gonna just cause it to fetch different instructions, probe the instruction cache for that, and voila, it still works. So somehow this need for kind of end-to-end also creates this, basically long iterative process that essentially is just like, okay, you show me the attack and only then I'm gonna do something. It's like, yeah, there are so many things that can be done that we're gonna go on for years. Doing this. So if you can elaborate a little bit on, how much of a concreteness do you expect from researchers before it becomes like, oh, this is an important problem, or this is easy to justify now as an important problem in my domain?
You can start.
Okay. So, oh, it's still there. So the value of content is increasing. So even if now some of those problems might not be felt as important, I really think that we should start looking into whatever attacks caches in this moment. I think it's critical mass, and we can't ignore it anymore. And in general, whatever looks at the memory hierarchy, and if we are talking in the context of system on chip, even what happens in network on chip, I actually have been, this is fun. I have been talking about we should look into side channel that concerned the network on chip immediately after we did some intensive evaluation of caches and things like that. And then 1 or 2, and basically the idea was dead there within the company. 2 years later or something like that, a guru who's here was presenting his newly accepted project into the T3S program at SRC, and they say, we have this, this beautiful thing that is looking at network on chip and how to create, actually, he was showing the existence of a covert side channel, very interesting, but he also was showing that's because it's an abstract concept that you can modulate the side channel, so you can add the encoding and you do all sorts of things to exploit the capacity of the channel and more. And I say, yeah, this is a great problem, but the point is the attacks are not very well engineered yet. So there is that level of engineering. I mean, if you do probing attack, Miles, right?
Yeah.
So you know very well that
I
the first order attack is very straightforward, actually.
Yeah, but my point is that basically, as academics, students want papers, right? And to some extent, it's easier. I mean, it's kind of counterproductive to make an attack extremely well engineered for a specific architecture, where we know that the general concept works, and probably like these 5 are attackable. It's just a matter of time doing it, and now the student has to spend 4 months porting the attack to different architectures and stuff like that. So like, do we need to do that?
No.
Or is it like,
No,
for
no.
this architecture, the other one has almost the same thing, so probably it's going to work?
No. It's not at that level that I was talking about. But the point is that even so, when attacks are very well engineered, look at the work that Yuval does at Adelaide, right? He has these great tools that you can deploy on a lot of architectures and start having a good grasp of what a cache side channel is, and he implements several attacks, and you can target several categories of platforms, not several platforms. Although sometimes things becomes really specific to, in the ARM world is actually quite interesting. So at some point I realized that I don't understand in ARM what a load instruction is, because depending on where the actual chip is manufactured, it actually has a slightly different behavior. So go figure all of this. But the point in general, to address also the other question that you had on the end-to-end attack, no, you don't need to do the end-to-end attack. Because the end-to-end attack is something that if attackers adopt your techniques, it will generate some monetary loss that it's not only felt, but it actually produces piracy or other things like this. And then at that point, the certification kicks off. And semiconductor industry, when, how do I say this? When you are not a supplier of security solution, Qualcomm is not, right? Really look into security if it is something that is mandatory for compliance, because otherwise you cannot sell your product in a certain market. So that's where I was. I hope it addressed some of.
Yeah, it does.
I guess one thing I want to address about the cache in one comment. I guess what I was really driving at, and with 10 minutes you're limited, is that there is this sort of pipeline of parts of the attack, and I want people to look at all parts to try to find the mitigations. Right, so we can look at the speculation, we can look at the channel, we can look at the injection points. So that's the first thing, right? I guess the second, I think now that we have that proof of pipeline, I don't think we need the continuing aspects of that. There will probably always be some points of resistance and where people may come back and ask, but I think now we have these sorts of proof of pipelines, that helps a lot. And then it is an non-trivial engineering. You can look at these cache attacks. I've seen the internal replications, and it does take a time to sort of build the art. But it is, David talked about, it's good to know how far you push a simulation, how realistic is it, because we do see some things that just fall apart. They work on paper, but when you push the implementation, it just doesn't happen.
So we are already into the breakout session, supposedly. So what, in the interest of time, we'll close out the discussion at this time and take a little break for about 10 minutes. So let's thank the speakers before that. So right after the break, we'll all head into the breakout rooms, which is 307.